In cryptography, to encrypt a data, a secret key is used. Based on how the secret key is generated and used, encryption is either symmetric or asymmetric. In symmetric encryption, same secret key is used by both sender and receiver, meaning encryption and decryption uses same key. It applies simple mathematical operations such as XOR, multiply, but on smaller numbers. Hence, it's quick. Whereas in asymmetric encryption, a key pair commonly called private and public key is used. Encrypted data with one key can be decrypted by other key. This key pair is mathematically related, so generating it and applying is complex mathematical operation. That's the reason it provides more security to data in comparison to symmetric encryption. At the same time, asymmetric encryption is slow because of the complex operations. Hence, these two techniques are used according to what data is to be encrypted and for what purpose. For example, TLS SSL protocol is an example where these two techniques are used. In short, a pre-master secret is sent by the client to the server securely after encrypting it with the server's public key. Then both client and server generates session key, which is later used for TLS record processing, where actual data is encrypted. Asymmetric encryption is also called public key cryptography. Today, as we securely access websites over HTTPS port, asymmetric encryption plays a significant role. As you recall in the previous slide, private and public keys are mathematically related. So, digital authentication is carried over public key encryption, whereas signature generation is carried over private key. Most of the implementations today rely on RSA or ECDSA for digital authentication and sign purpose. Due to implementation challenges for public key cryptography algorithms, they open door for side channel attacks as well. Importance of cryptography design. Statistics say in last 10 years, HTTPS traffic almost doubled. So attacks on HTTPS session is increasingly common where a malware could be designed to steal private key which is critical to HTTPS session. Side channel attack is a technique which is still under research to exploit various implementation defects through its physical parameters, meaning supply current, EM radiation response time of a system could be studied to analyze the pattern of how the system behaves to unlock a secret key bit by bit. Generally, these experiments point out faulty implementation most of the times. For example, multiple experiments have been done to demonstrate how side channel attack can be done over ECDSA algorithms. One common reason it is exploitable is due to the usage of nonce value used in sign generation. Edwards curve digital signature algorithm, also called EdDSA, is a variant of SNOS signature system with Edwards curve. Earlier, RFC 7748 introduced two elliptic curves, namely curve 25519 and curve 448. These two curves aim two things. 1. Constant time implementation. 2. Exception free scalar multiplication. This is important to resist from side channel attack, specifically cache and timing attacks. RFC 8032 in standardized Edwards curve instances based on hash function and other elliptic curve parameters, and they are ED25519, ED25519 CTX, ED25519PH, ED448 and ED448PH. Here CTX means context and PH means prehash. Technical advantage of EdDSA is that it doesn't use nonce, meaning portion of private key after hash after hashing it, determines a nonce instead of using any random source. Hence, sign is more deterministic. Edwards curve 25519 is widely used and there are many applications supporting it. For example, OpenSSL, SSH, TLS 1.3, etc. They support them. EdDSA offers several technical advantages over other algorithms like RSA and ECDSA. Here are its key benefits. 1. EdDSA performs faster signature creation and verification than traditional algorithms like ECDSA and RSA. Number 2, it has no variable time operations, so reducing susceptibility to side-channel attacks. Number 3, it is deterministic in sign generation, meaning same message always results in same signature because no random source is used. Number 4, EdDSA achieves same or better security than ECDSA for the same key size. For example, to achieve same strength of same security strength of ECDSA, curve SECP 256R1, curve 25519 needs only 128 bit. In DPDK, we propose to support public keygen, sign, and verify operations. At present, our 5 curve instances that RFC 8032 proposed are implemented. Also, we have test vectors from same RFC verified through autotest as well. And the same test vector is used in CryptoPerf application as well for benchmarking PMD driver performance. Getting into details of implementation, to manage EDDSA specific crypto session, and new enumerations are added following standard specification from IANA TLS supported groups. They are curve ID 29 and 30, 29 for ED25519 and 30 for ED448. So when we create session object, we need to use one of these curves. Next, for crypto operation, Edward curve instances are accounted and new EDDSA specific parameters implemented in crypto op now. Also, a new asymmetric flag is introduced to support compressed form of public key um, used in Edwards curve in comparison to other elliptic curves. Here is an example code of public key generation using EDDSA in DPDK. At first, session transform is created for Edward code 25519. Then private key is given as the input parameter. Next, a crypto op object is created wherein key exchange type is set to pub underscore key underscore generate. Also, a symmetric flag for compressed form of public key is included in crypto op. After enqueuing and dequeuing crypto op, result crypto op will have public key generated in its ECDH member, basically in pub underscore key variable in it. Here is an example of EDDSA sign operation using curve ED25519. We need to give both private and public key as session parameters. Then crypto op type is chosen as a sign and plain text is given as an input. Then as we choose instance as ED curve 25519, context value is not required. So we just set it to 0. And finally, the result sign data will be in the output buffer. Here is similar example for verify operation. Similar steps as in sign, but some differences are here. Like in session parameter, only public key is used, and in crypto op, both plain text message and the signed data are given as the input, and curve instance is set. After enqueuing and dequeuing successfully, signature can be valid if status field in result op is actually RT crypto op status success. Now let's see some performance study that we carried out in proposed DPDK support. If you look at EdDSA sign and verify algorithm design, a symmetric hash operation occur in multiple places throughout the asymmetric operations. Symmetric operations is expensive here, and proper hardware offload is helpful to free up CPU cores. In our hardware offload experiments, we find 30% better sign performance for EDSA in comparison to ECDSA. Similarly, verify performance is 12% better, and in software experiment, meaning no without hardware offload, for example, in TLS handshake protocol performance test, we observed it is same as ECDSA. So in summary, EDDSA offers better security, that is, its resistance to side channel attacks, better performance, meaning faster sign and verification with a smaller key and signature size, and simpler implementation, that is, deterministic signatures it can provide without using any random source, comparing to alternatives like ECDSA. Due to its strong security properties, efficiency, and simplicity, modern cryptographic protocols like TLS 1.3, SSH, DNSSEC, etc., has support for EDDSA. At last, future proofing against emerging threat is also critical for long-term security, especially in the age of emerging technologies like quantum computing. Until those are in wider deployment, we need to be most secure and stronger with protocols like EDDSA as a shield in our classic computing today.